Hello all, welcome back to my YouTube channel all about VLSI. In this video, we are going to discuss about transaction layer. Basically, we are going to discuss about all the protocol layers which we are going to have in PCIe, and we are going to more discuss about transaction layer. What is this particular transaction layer and all we are going to discuss in great detail, right? Now, so coming to PCIe, basically it is going to have different kind of layers. One is transaction layer and another is data link layer. Next is physical layer. So let's say suppose if I have a master and a slave like this. Now this master is going to send the data or the packet through the three different layers, where the first layer it is being involved is the transaction layer, and from the transaction layer the packet is moved forward to the data link layer, and from this particular data link layer is going to be forwarded to the physical layer. So this is the flow which is going to happen, and from the physical layer my receiver is going to receive the data packets, and again it is going to give back to the data link layer, and next from the transaction layer it is going to give it to the software or the OS. So this is how the basic data flow is going to happen. So basically every PCIe device, root complex, switch or endpoint, so it may be anything. It might be a root complex, or it might be a switch, or it might be endpoint. These are going to implement the same three layer stack. These are going to implement the same three layer stack, and the packets are going to travel down the stack to transmit and back it up. Okay, so this is the process which we are going to have. Now coming to the transaction layer, it is going to create and it is going to decode something known as TLPs, and it is going to manage the address spaces, and it is going to apply the QoS ordering, and it is also going to control. It is also going to have the flow control credits. So what do I mean by this? That is what we are going to discuss in this particular session. And in our upcoming sessions, we are going to discuss what do I mean by data link layer and what do I mean by physical link layer and all we are going to discuss. Okay. Now, coming to transaction layer, let us first of all try to understand the packet of TLP. So in transaction layer, this is what the packet structure going to look like. So I'm going to have a header, which is basically 3 to 4 data words, and next is payload, your actual payload. It might be 0 to 1024. Okay, 1024 data words, and next is ECRC, which is optional, one data word. So coming to data word 0, this is going to have this is nothing but my header structure which I'm going to have. You can see it is 3 to 4 data words. This is a 4 data word header structure. Okay. Now, so the first field is format, which is of 2 bits, and next is type, which is of 5 bits. Next, these are reserved. Next is TC. Basically it's nothing but traffic class, and this is again reserved. Traffic class is 3 bits, and next TD, and next is EP. Next, after that we are going to have something known as attribute. Next is reserved. Next is length, and next is length. Okay, and followed by requester ID, tag, last BE, first BE. Next is address 63 down to 32, which is basically this is a 64-bit address, and 64-bit address is basically split into 32 bits and 32 bits. And next is, after this is nothing but my header, which is basically 4 data words. And next is my data payload. It might be 0 data words or 1024 data words. Okay, and next is ECRC. Now over here, first of all, let us try to understand a few more things, and let us come back to what do I mean by format and type, so that we will able to understand what is exactly happening. Now, coming to the transaction layer roles and responsibilities, this is the topmost protocol layer, and it is only layer which is aware of transaction semantics. It is going to know what is memory, or what is IO, or what is configuration and messages, and it's where every packet is born or finally consumed on the receiver. Now, what are the key responsibilities? It is going to build the transaction layer packets, whatever the actual data which we are going to have, or the actual data packet we are going to have, it is going to create its own frame like the header and ECRC and all. It is going to create it, and it is basically address space aware. So what do I mean by address space aware? This is what we are going to discuss in our particular session, in this particular session. And next is flow control credit based. So what do I mean by flow control and all also we are going to discuss. And what do I mean by virtual classes and traffic class we are going to discuss in this particular session. And what is requester or completed tracking. And next is optional end-to-end CRC. This is what we are going to discuss. Then after we will come back to this TLP structure or the packet format. Then we are able to understand what exactly the meaning of each and every particular field. Now, coming to the different kind of address spaces, first of all, let us try to understand what are the different kind of address spaces which we are going to have. Assume if I'm going to have a simple GPIO controller, let's take a simple GPIO controller. This particular GPIO controller is going to have different internal registers, like let's say suppose data register, or let's say suppose direction register, and next is let's say suppose alternate function register. Like this, I'm going to have different kind of registers inside my GPU controller, and each register is going to have its own kind of responsibility. Here in this case, data register is basically used to hold the data. Direction register is going to basically decide the direction of the physical GPIO pin and all. Okay, so if my processor wants to access the GPIO pin, and if it needs to configure the GPIO pin to an output or an input, it is not going to directly access the GPIO pin. It is going to configure this particular direction register. Or let's just suppose this GPIO pin to, if my processor wants to configure it to act as a UART pin, so it can do, like it can have an alternate function. So how it is going to configure this particular pin? It is going to basically update this particular register. Okay, so processor or the OS is not going to directly access the physical pins, but it is going to access the internal registers which are present inside your controller. Not only GPU controller register, think about any particular PCA compliant device, or any real-time IP where we are going to have. And if you want to configure any particular things, you are going to have internal registers set. Okay, this is what normally we have. Now, this particular internal registers, if my processor wants to access, let's say suppose data register, how it is going to access? It is going to access it using the address. So this data register, let's say suppose it has a base address of 8, and let's say suppose this direction register is having the address as C. Okay, and the difference here is 4. This is nothing but my offset. Okay, so every particular internal register has its own address, and the offset is nothing but the next address. Okay, so this address, using this address only, my processor or the OS is going to access this particular registers, and this registers will come into the space which is known as memory space. So if my processor, let's say suppose if my address is 8, if my address is 8, and the TLP type or the format or the type field, if it is equal to 00, then my processor is going to access the internal registers. Let's say suppose we are going to have some space which is known as configuration space. What do I mean by configuration space? In our previous sessions also we have discussed that every particular PCIe compliant device is going to have its own space, which is going to contain different kind of fields like vendor ID, device ID, and different kind of attributes and all. Different kind of information it is going to have. Whenever my OS or the processor is going to read this particular configuration space, it is going to come to know entirely about the device, right? So this is why we are going to use a configuration space. Now let's say this configuration space is also going to have a base address as 8. Then how I am going to differentiate between this particular address and this particular address? So the register address is also 8, and the configurations space address is also 8. How I'm going to differentiate which particular address I'm going to refer to, or which particular address space I'm going to refer to? For differentiating this, I'm going to have something known as format. So this format is going to basically decide what kind of address space I'm referring to, whether I'm referring to the memory space or whether I'm referring to the configuration space. This format is going to tell me. Okay, so this is where you can think of using a format. And next is IO space. So what do I mean by this IO space? Also, we are going to discuss now. Yes, so this is what I was saying about. We have different kind of spaces like memory space, IO space, and configuration space. So in the memory space, the primary space, this is nothing but the primary space in PCIe, and it is used whenever the CPU or another bus master reads or write the data to a device, like control registers or FIFO or DDR or DMA buffers, or you can think of this particular example, data register or direction register or alternate function register. If I want to access these registers, I'm going to access the memory space. And next is configuration space. This is what I was discussing about. So every PCIe function is going to have a dedicated 4096 bytes of configuration space holding vendor ID, it is going to hold device ID, and it is going to have everything the OS needs to discover and set up the device. So this is nothing but my configuration space, right? Now coming to my IO space, it's a legacy space inherited from PCI. So PCIe is not going to have any, PCIe compliant devices are not going to have any kind of IO space, but PCI devices, the older devices, are going to have this kind of input output space where the CPU is going to access the input output ports instead of memory. So if I want to access this particular port, now what we are going to do, we are going to configure the register. But in the case of your IO space, the processor or the OS is directly going to access this particular port instead of having this memory spaces. Okay, that is nothing but your IO space, and this particular PCIe is backward compatible, so that's the reason I'm going to access it. Yeah, this is what I was saying about legacy access and device discovery. So a legacy address space inherited from older PCI systems, instead of accessing memory, the CPU access input output ports directly, and it is only kept for backward compatibility. And PCIe still supports input output transactions, so older softwares and drivers keep working unmodified. And next is configuration space, where every PCIe function carries 4096 bytes of configuration space, and the answers the OS needs to power on. So, like which particular PCIe device exists, and what is the vendor ID and device ID, and what is the memory requirements, and what is the interrupt capability, and all, I'm going to come to know from this particular configuration space. So this is nothing but your memory aware. So or address space aware. This is the first responsibility of my PCIe. Okay. Now, so routes by memory input, output, or configuration on messages space depending upon the TLP type. Next is flow control or credit based. Let's try to understand what do I mean by flow control or credit based. So coming to what exactly is flow control? Let's say suppose I have a root complex or a sender and a endpoint where this particular endpoint is only having 4 slots to store this particular packets. Okay, and let's say suppose a receiver has a finite buffer space, and if the transmitter sends faster than the buffer drains, packet obviously will not have anywhere to go. And the PCIe cannot never allow packet loss. In PCIe, it is not going to allow the packet loss. So here, what is going to happen is, for avoiding the packet loss, what is that we are going to have is, we are going to have something known as credit. So my transmitter is going to know how many credits are left, or how many space or how many slots are still available for sending the packets. Okay, so depending upon this credits, my transmitter is going to decide whether to send the data or whether not to send the data. So PCIe cannot tolerate packet loss. So before sending, the transmitter must first check whether the receiver actually has a room or not. And that check is nothing but my flow control using the credit based mechanism. So credit based flow control, a credit represents a available space in the receiver, and no credit means there will be no transmission. If there is no credit in the receiver, then obviously transmitter is not going to transmit. And if there is available credit means the transmitter is clear to send. So first endpoint has 16 TLP buffer entries, and next it announces that I have 16 credits. Next root complex is going to send the 16 credits. So each send unacknowledged TLP consumes 1 credit, and each freed buffer slot returns 1. So keeping the link exactly as full as receiver can handle. So the result is obviously there is no packet loss. No. So this was the second responsibility. I mean the third responsibility, which is nothing but my flow control credit based, where it is going to track receiver buffer credits. So it never sends a TLP the link partner can't observe. Okay. Next is virtual channels and traffic classes. So let us try to understand what is this fourth responsibility of transaction layer. So let's say suppose if I'm going to have only a single queue where everything is going to wait. So for example, if I'm going to have a FIFO where I'm going to have DMA packets lined up, and next an interrupt which was given, and next I'm going to have DMS again. So not all the traffic has equal urgency. Interrupts need to be served quickly. So let's say suppose receiver has given an interrupt to the processor, but before interrupt, this many packets are still pending. So this will take time to process. Then after interrupt will be given if I'm going to follow a single queue. Okay. Now what is going to happen? Interrupts should be served quickly before this DMA. So a single FIFO queue can't express priority. It only expresses arrival order. So larger DMA transfers can dominate the link for many cycles. So PCI's answer. So what is that we are going to have? So due to this, a single queue, what is going to happen is this urgent interrupts will be stuck behind the late happening this DMA transactions and all. It is going to wait for so many number of cycles. So what is that PCI is going to do is PCI is going to label the packets by priority, which is known as traffic class TC. Okay, so each packet will be labeled with its own number, which is nothing but your traffic class number. Then it is going to give each priority its own queue, which is nothing but your virtual channel. Okay, let us try to understand what do I mean by traffic class and what do I mean by virtual channel. So a traffic class, it's like a priority label. It's not a queue. So every TLP header we have seen, right? The TLP header. Let me show you. Yes, this one, the TLP header. I'm talking about TC. This one I'm talking about, which is nothing but your traffic class. So every TLP header is going to carry a 3-bit TC field. 3 is nothing but 2 power 3, which is nothing but 8 priority, 8 possible priority levels. And traffic class marks the packet. It doesn't route it anywhere by itself. For example, if the TLP header of a certain packet is labeled as 010, other header fields like FMT, type, length, address, etc. are going to remain the same. Okay. So traffic class TC2, that means this packets belong to priority level 2. Okay. Let's say suppose if I'm going to have 8 traffic classes TC0 to TC7, like this I'm going to have different kind of traffic classes where TC0 is given the highest priority. Let's say suppose if my processor wants to or the OS wants to process a particular packet, which packet it is going to process? Obviously the packet which is having the high priority only it is going to process. For example, if I'm going to have a DMA packet and a MSI interrupt, so which particular packet will be processed by the OS? It is obviously look for the DMA packet because TC0 has the highest priority compared to MSI interrupt which is having TC3. So we are going to have a single link, same link, different labels. That's it. The packets now carry distinct priorities rather than downstream logic and actor. Okay. Now, that was about your traffic class. Traffic class is kind of a tag. You are going to keep it to a particular packet so that that particular packet is going to act. Now, next is virtual channels, where we are going to have separate queues on a single wire. So, a virtual channel is the real queue inside the transmitter and the receiver, and there is still only one physical PCI link. We are going to have only one PCI link, but we are going to have a group of channels which is being implemented inside your transmitter or receiver, where I'm going to have one particular channel. Let's say suppose VC0. This channel is going to hold all the different kind of packets, and this particular channel is going to have one particular packet, and this channel is given the high priority. So whatever the packets which are included in this particular channel will be sent first using the transmitter arbitration, and it will be sent on the physical link, and after this the other channel packets will be sent accordingly. Okay, so channel is kind of a grouping all your packets, and each packet is going to have its own uh, TC, okay, traffic class tag, and you are going to group everything in inside your channel. That's it. Okay, this is nothing but your virtual channel and traffic class. So we are going to our particular transaction layer is basically address space aware and memory space, and next is credit based, and next is traffic class plus virtual channels. So as I've said you, TLP types, I'm going to have different kind of types. One is memory, the address space may be a memory address, or it may be IO, or it may be configuration, or it may be message, or it may be completion. Okay. So memory, we are going to have memory read, memory DLK, and memory write. Okay, memory locked. So where bulk data transferred to or from the device, memory or host RAM. And next is IO, where I'm going to have IO read and IO write and so on. Okay. And I'm going to have something known as posted and non-posted, where posted is nothing but you send the packet and you forget about it and no completion is expected. For example, you can have it for memory write or message, whereas for the non-posted, you're going to expect, the transmitter is expect the requester acknowledgement from the requester. So requester needs a data or a status back. A completion TLP must follow it. For example, you can use it for memory read or IO read write or configuration read write. Okay. So this was about your transaction layer, where we have discussed about this particular type and format and transaction class, and yeah, this is what we have discussed it. So our format or type, it's basically 7 bits. It is going to decide what is the header length, what is a payload, and what is a TLP class, whether it is memory or IO or config or message completion. And next is attribute. So it is going to decide the traffic class and relaxed ordering, and no attribute hints. This we are going to discuss later in great detail when we are going to implement it. And next is TD. So if the TD is equal to 1, ECRC, the error correction mechanism, is appended. If it is equal to 0, error correction mechanism is not appended. And EP is going to basically tell whether the packet is poisoned or it is not poisoned, or it's a good packet. And next is length, which is going to tell the exact payload size in data words. And requester ID or the tag, where it is going to basically originating from BDF, which is nothing but bus device function, where exactly this particular, what is the ID of the requester who is requesting for the packet and all. And next is the actual address. It might be 32 bits or the 64 bits. So this is nothing but my exact complete TLP packet which I'm going to have. Yes. So that's about the transaction layer, and we are going to still discuss about the in detail fields. So when we are implementing it, and depending upon the requirement, we are going to discuss in great detail about each and every particular fields. And this particular session is basically give you idea overview of exactly how the packet transaction layer packet is going to look like and all, and what is the responsibilities of this particular transaction layer packet. Okay. Yes. So that's all about this particular video. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.